Hello everyone, I am Dhara Kansara. I will discuss synchronous counters in this video. I will cover the following topics: what is the synchronous counters, synchronous up counters, and synchronous down counters. In my previous video, I have already discussed what is the counter, what is the difference between asynchronous counters and synchronous counter. So simply, counter will count the clock pulse. And what is the difference between asynchronous and synchronous counters? In asynchronous counter, we will not apply clock simultaneously. Means output of one flip-flop will be given to the clock of the next flip-flop. In a synchronous counter, the clock inputs of all the flip-flops receive the common clock. Now we will see how to design synchronous counters. So to design synchronous counters is very easy. Compared to asynchronous counter, the design of these counters will be easy. There are few steps we have to follow to design synchronous counters. So firstly, I will discuss that 5 steps to design synchronous counters, and these steps will be common for all the types of synchronous counters. These steps are the step number 1, decide the number of flip-flops are required. So suppose in the question that is given how many bits you have to use to design the synchronous counters. So first step is we have to decide the flip-flops. So number of bits is equal to number of flip-flops. Okay. What is the second step? Excitation table of given flip-flop. So in the question, if flip-flop is given, then there is no need to decide the flip-flop. But suppose in the question flip-flop is not given, then you can take any flip-flop, either JK or P or D. So first, in the second step, if flip-flop is not given, then you have to decide the type of the flip-flop to design the synchronous counters. Now, step number 3, you have to draw the state diagram and then circuit excitation table. Step number 4 is obtain simplified equations using K-map. And the last step number 5 is we have to draw the logic circuit diagram using logic equations. Okay. So suppose I want to design 2-bit synchronous up counter using T flip-flop. Right. So now we know what is the step 1. We have to decide number of flip-flops. Here 2 bits are given. Okay. So number of bits is equal to number of flip-flops. So 2 flip-flops are required to design synchronous up counter, 2-bit synchronous up counter. Then step 2, excitation table of given flip-flop. Here T flip-flop is given. So excitation table we have already discussed in the last lecture. What is the excitation table? I mean present state and next state QT and QT plus 1 as input and T as output. Now step number 3, state diagram and circuit excitation table or state table. This is the state diagram. As I told you, 2 bits are given. So total possible combinations, maximum possible combinations will be 4. Number of states will be 4. Maximum states will be 4. And that are 0, 1, 2, 3. 4 states are there, means 0, 0, 0, 1, 1, 0, 1, 1. We can say in decimal equivalent 0, 1, 2, 3. So total 4 states are there because I am using 2 bits. Maximum 4 possible combinations, maximum 4 states will be there. This is what state diagram means. First state is 0, 0, then next state is 0, 1, then next state will be 1, 0, and the last state is 1, 1. Then again flip-flop will restart at this count, after this count. So again, it will start counting from 0, 0. This is what up counter, as we have seen in asynchronous counter. In up counter, counting will start from lower number. I mean, it will count from 0, 0 in 2-bit, 0, 0, 0, 1, 1, 0, 1, 1. And as we have discussed in asynchronous counter, it will restart. Counter will be restart after the last state. Okay, so this is the last state 1, 1. Then again it will restart from 0, 0. Fine. Now, so this is what state diagram. Now we will see circuit excitation table or state table. This is also known as state table. In state table or in excitation table, as we have discussed, this is what excitation table. We have to cover present state, next state, and input T. So circuit excitation table means here in our circuit, we have to use 2 flip-flops, right? For that circuit, we require 2 flip-flops, 2 T flip-flops. So circuit excitation table means I will design the table for that circuit. In that circuit, I am using 2 flip-flops. That's why I have written 2 present states, 2 next states, and 2 inputs. I mean T1 and T2. So for T1, here Q1 and Q1 plus. Okay, these are the states. Means Q1 is present state, Q1 plus is the next state for T1. Q2 and Q2 plus, these are 2 states for this T2. Means for T2 flip-flop, for the second flip-flop, Q2 is present state and Q2 plus is next state. Because what we have to do, present state, next state, and flip-flop inputs. So these are the present states. Flip-flop, present state of flip-flop 1, present state of flip-flop number 2, the next state of flip-flop number 2, and next state of flip-flop number 1, like this way. Now, here you can see 2 states are there. I mean, Q1 and Q2 are there. So 4 possible combinations, maximum possible combinations will be 4, 0, 0, 0, 1, 1, 0, 1, 1. Okay. So suppose this is the present state, right? 0, 0. Then what will be the next state? We will refer this state diagram to write to complete this table. 0, 0 is the current state, I mean present state or current state. You can see here, this is current state. So in the diagram, what is the next state? Arrow is going like this way, right? Right side. So this is the, suppose this is the current state, then next state will be 0, 1. So this is what next state. So I will write here 0, 1. Now this is what present state. Present state is suppose 0, 1. So next state will be 1, 0. So that's why 1, 0 I have written here. Suppose 1, 0 is the present state, 1, 0 is the present state, then next state will be 1, 1. So I have written here 1, 1. And suppose 1, 1 is the present state, you can see here, then next state will be 0, 0. So like this way, we have to write this, we have to complete this table. So you have to draw the state diagram for this table. Now, we will refer this excitation table of the T flip-flop. Here, what is given? Present state and next state. So suppose present state is 0 and next state is 0. At the same time, T is 0. Here you can see, if present state Q2 is 0, next state Q2 plus is 0, then T2 will be 0. We will refer this excitation table. Suppose Q2 present state is 0, Q2 plus next state is 1. So for 0, 1, T will be 1. For 0, 1, T will be 1. Here T2. That's why Q2, Q2 plus and T2. Now Q2 is 1. Q2 plus is 1. At the same time, both are 1. This T will be 0. If both states are 1, then this will be 0. Like this way, we have to complete this also. Okay. Suppose I will take one example. Suppose Q1 is 0. Q1 plus is 1. So 0, 1 gives 1. Here you can see 0, 1. We'll write here 1. So to complete this table, we have to refer this state diagram as well as the excitation table of given flip-flop. Okay, fine. Now what we'll do? Step number 4, obtain simplified equations using KMAP. So how we will draw the KMAP? Using this table only. Now you know how to draw the KMAP, right? We have already discussed in the previous videos. This is what output T2 and T1. So I will draw KMAP for T2 separately. Then I will draw KMAP for T1. What are the inputs? Q2 and Q1. Present state will be inputs. Please, you have to remember this thing. In the KMAP, we will take these inputs only. Present state as an input. You can see here, we will take present state as an input. Don't take this next state in KMAP. Okay, fine. So Q2, Q1, two variables are there, two inputs are there. So 4 blocks are there in KMAP. Okay, and input variables are Q1, Q2. So 0, 1, 0, 1. Okay, so for these combinations, Q2 is 0 and Q1 is 1, output will be 1. And for this combination, 1, 1, output will be 1. So here we'll put 1, 1 in this block. This is what? Q1 is 0, Q1 is 1, and for this block, Q2 is 0 and Q2 will be 1. So we'll make a pair of these ones. Okay, so equation T2 is equal to Q1 because here Q1 is constant. So T2 is equal to Q1. Similarly, we will design a KMAP for T1. You can see here all output mean terms will be 1 for this combination 0, 0, 0, 1, 1, 0, 1, 1. For all these combinations, output will be 1. So you can see here there will be a 1 in all the KMAP cell. So if we will make pair of 4 ones, then we'll get equation because T1 is equal to 1 because here in all the cells output will be 1. Okay, it will follow OR logic operation. So this is what T1 is equal to 1. Now there is a next step number 5. Draw the circuit logic diagram from these equations. T2 is Q1 and T1 is equal to 1. So we know now we have to use 2 flip-flops, 2-bit synchronous counter. For 2-bit synchronous up counter, we will use 2 flip-flops. T1, Q1, Q1 dash, T2, Q2, Q2 dash. And this is what? Clock. This is synchronous counters. So clock will be given to simultaneously, or else we can say clock is the same for both the flip-flops. Fine. Here T1 is equal to 1. That's why here logic 1 will be connected to this T1. What is T2? T2 is equal to Q1. So this Q1 will be given to T2. Right? Here we will get output Q1 also. Okay? And then Q2. So this is what logic circuit of synchronous 2-bit up counters using T flip-flop. You can design it by D flip-flop as well as by using JK flip-flops. Steps will be same. The steps will be same. Okay. So this is what 2-bit synchronous up counters. Now suppose you want to design 3-bit synchronous up counter, steps will be same. This excitation table will be same. Okay, the state diagram will be different. Why? Because here 3 bits are there. For 3 bits, we will use 3 flip-flops. That's why there is a slightly change in this excitation table also. 3 flip-flops will use T1, T2, T3. And here in this state diagram, you can see count will start from 0, 0, 0 and will end by 1, 1, 1. Means 0 to 7. 0, 1, 2, 3, 4, 5, 6, 7. This is up counter. That's why arrow is given in the forward direction. So last count is 1, 1, 1. After this count, flip-flop will reset. Flip-flop will start counts from 0, 0, 0. This is what circuit excitation table. This table will be filled by same procedure as we have discussed in 2-bit synchronous up counter. Okay, the design will be simple. You have to write present state, next state, and flip-flop input. T1, T2, T3. Then Q1, Q2, Q3 present states, Q1 plus, Q2 plus, and Q3 plus are the next states. Then what you have to do? You have to write the combinations, possible combinations here. This is 3 bits, so maximum possible combinations will be 8 from 0, 0, 0 to 1, 1, 1. Now we will refer this state diagram. Current state is 0, 0, 0. Next state will be 0, 0, 1. I will write next state here. Then suppose current state is 0, 0, 1. The next state will be 0, 1, 0. Okay. So this in the next state, we will write these combinations and in this sequence only. Okay. Fine. So now we'll draw K-map. From the K-map, we will get circuit design. Here you can see T3 is equal to Q1, Q2, T2 is equal to Q1 and T1 is equal to 1. That's why T1 is equal to 1, logic 1, fixed logic 1 is given to T1. Then T2 is equal to what? Q1. So this Q1 I am applying to this T2. Then T3, Q1, Q2. So T3, Q1, Q2. This is what? AND operation. Q1 dot Q2 and is given to T3. So this is what? 3-bit synchronous up counter using T flip-flop. Similarly, 3-bit synchronous up counter using JK flip-flop. This is for your reference. I have taken for your reference only. The circuit will be like this way. Only the difference is here we are using T flip-flop, but instead of T flip-flop, we will use here JK. You know the difference between JK and T. Both the inputs are common. Means in JK flip-flop, from the JK flip-flop, we can design T flip-flop like this way. All these two inputs will be connected to each other in T flip-flop. Fine. Now next 4-bit synchronous up counter using T flip-flop. Steps will be same. You have to follow the same steps. T flip-flop, so excitation table of T flip-flop, 4 bits, so 4 flip-flops you have to use. Then this is what state diagram, 4 bits are there. So possible combinations will be 16 from 0, 0, 0, 0 to 1, 1, 1, 1. This is what excitation table. Then you have to design K-map. Then from that you have to design circuit. Fine. Now this is what 4-bit synchronous up counter using JK flip-flop. Circuit will be same. Instead of T, we will use here JK. Okay. Now we will see synchronous down counters. Again, steps will be same. You have to follow the same steps in each and every synchronous counters. So step 1, you have to decide the flip-flops. 3-bit synchronous down counter, 3 bits is given. So 3 flip-flops you have to use. Step number 2 is write excitation table of T flip-flop. In step number 3, what we'll do? Draw the state diagram and circuit excitation table. So here 3 bits are there. So maximum possible combinations will be 8. Maximum states will be 8. Now down counting, this is what down counter. 3-bit down counter. So we'll move in reverse direction in this state diagram. So counting will start from say 0 0 0, the next state will be 1 1 1, the next state will be 1 1 0, like this way. So come to this table, we are using 3 flip-flops, that's why present states will be Q1 Q2 Q3, next state will be Q1 plus Q2 plus and Q3 plus, and this is what T1 T2 T3, because 3 flip-flops we are using. Now if current state is 000, here you can see in this state diagram, the next state will be 111. If current state is 1, the next state will be 110. If current state is 110, the next state is 101. Like this way we can design here, we can write, we can fill this table. Then what about this T3, T2 and T1? For that, you have to refer excitation table of the T flip-flop, which we have written in the second step. So you have to refer this table. Here you can see previous state is 0 and next state is 0, then T is 0. So like this way, you have to refer that table and fill these things. So Q3 is 0, Q3 plus is equal to 1, then T3 will be 1. So we will refer the excitation table of the T flip-flop for this thing. Fine. Now the step 4, find logic equation from the K-map. So we'll draw K-map from this table for T3, T2 and T1. We will draw K-map for T3, T2 and T1. You can see here, this is what T3, T2 and T1. So by solving this K-map, we will get T3 is equal to Q2 dash and Q1 dash. T2 is equal to Q1 dash and T1 is equal to 1. You know, we have already discussed how to solve, how to write the Boolean equation from this K-map. We have already discussed in the previous video. Fine. Then next state, that is create circuit diagram. So from this logic equation, we will design synchronous down counter. In that we are using 3 T flip-flop. So T1, here you can see T1 is equal to what? 1. So here T1, in T1 we are applying fixed logic 1. Then what about T2? Here T2 we are getting Q1 dash. So you can see here in this T2 we are applying Q1 dash. Then what about T3? T3 is equal to Q2 dash and Q1 dash. Means we will use AND logic here, and in the AND gate we will give Q2 dash and Q1 dash. You can see here, this is AND gate, Q2 dash and Q1 dash we are applying, then this output will be given to T3 and we'll collect output from Q1, Q2 and Q3. So like this way, we can design synchronous down counters. It will count simply in the reverse direction. Okay. Now this is what timing diagram. You can see here, we are collecting output from Q1, Q2 and Q3. And here you can see, this is what Q1, Q2 and Q3. Okay, as we are applying clock, negative edge clock pulse. So at this edge, whenever clock will move from 1 to 0, at this edge, Q1 will change its state, Q2 will change its state, and Q3 will change its state. Initially, it is 0, 0, 0, but after applying this clock, it will be 1, 1, and 1. Then you can see here, 0, 1, 1 means this is what? This bit is LSB bit and Q1 is LSB bit and Q3 is MSB, means 1 1 0 actually. So 1 1 1 and then it will count 1 1 0, 7 6 4 3 2 1 and then again 0. Then it will reset and counting will start from again 1 1 1 1 1 0, like this way. Okay. So this is what? Synchronous down counter. Now, this is what synchronous 4-bit down counter. So 4-bit down counter means we will use 4 flip-flops, and similar steps we will use, and we can design the circuit like this way. And here we are using JK flip-flop. Okay friends, thank you.